Newton's Law of Universal Gravitation. Newton's Law of Universal Gravitation explains the force of attraction, or describes the force of attraction between any two objects in the universe that have mass. Recall a few features of gravity. Firstly, the force of gravity is an attraction between two different objects. Any object that has mass will exert a gravitational attraction on another object that has mass. This law is called a universal law because it applies for all objects in the universe, not just objects here on Earth. Let's take a look at what Newton's law of gravitation looks like. Here is the equation. It says that the force of attraction between any two objects with mass is equal to some constant, the universal gravitational constant, times the mass of the first object, times the mass of the second object, divided by the distance between the objects squared. Strictly speaking, distance is measured from what's called the center of gravity of the two objects. But for most geometric objects that have a regular geometric shape, like a sphere, the center of gravity is found in the geometric center of the object, as long as it has uniform makeup throughout. So for example, if the Earth were one of our masses, the center of gravity for the Earth would be the center of the Earth. Force in this equation would be measured in units of newtons. And remember, a force is just a push or a pull. So in this case, gravity is an attractive force. It is a pull that is felt by both objects. That pull would be measured in the units of force, which are newtons. The universal gravitational constant, capital G, is just a number that's used every time we use this equation. So we would substitute 6.67 times 10 to the negative 11 for that constant in the place of capital G. The mass 1 is the mass of the first object, m2 is the mass of the second object, and these masses must be measured in kilograms. The distance between the centers of the objects would be measured in units of meters. By following the correct convention for units, we would arrive at units of Newton for the force of attraction. Don't confuse this force of attraction with the value of little g for acceleration due to gravity. Acceleration due to gravity near the Earth's surface is 9.81 meters per second squared. But that is an acceleration. Newton's law of universal gravitation tells us the strength of the force of attraction that exists between two objects it gives us a force measured in units called newtons. There are a couple of things that you can tell simply by looking at the equation here. For example, if either mass 1 or mass 2 were larger, if we substituted larger numbers in the formula for either of these masses, then the force of gravity would increase. So we could say that force is directly proportional to the masses. In fact, the attractive force is usually only large enough to be noticeable or significant when one of the masses is very large, say the size of the planet Earth. Secondly, when the distance between two objects increases, the strength of the gravitational attraction decreases. It goes down. So the farther apart two objects are, the weaker the force of gravity between them. We would say that there is an inverse proportion between the force and the strength of attraction due to gravity. What this means is that as distance increases, force decreases with the square of the distance. So if two objects are 2 times farther away, then the force would be 4 times weaker. If the distance between the objects were 3 times farther away, then force would go down by a factor of 9. Let's look at a sample problem now that involves this equation. The question is, what is the gravitational force of attraction between a 50-kilogram girl and a 60-kilogram boy if they are sitting 2.5 meters apart in a physics class? Well, let's use Newton's law of universal gravitation to find the answer, which says force equals capital G times m1 times m2 divided by distance squared. So first, we'll substitute in the information given in the problem. Big G equals 6.67 times 10 to the negative 11. We can allow m1 to be the mass of the girl, or it could be the mass of the boy. It really doesn't matter. We just choose one to be mass 1, the other object to be mass 2. So 50 kilograms would be the mass of the girl. 60 kilograms would be the mass of the boy. They're both in units of kilograms, so we have the units that we need. The distance between them is 2.5 meters. Distance should be measured in meters, and that distance must be squared. A common mistake with this equation is that students forget to square the distance. Be sure that you square distance when using this formula. All right, so now if we actually do the calculation, I'll take my numerator, 6.67 times 10 to the negative 11 times mass 1 times mass 2 divided by the distance between them squared. So the force of attraction between the boy and the girl is a very small number. 3.2 times 10 to the minus 8 newtons. This makes sense, as we said that the mass of the object must be very large before the force of attraction between two objects becomes noticeable. Now, I'm going to give you a practice problem. Pause the video, try and solve the problem on your own, and when you're finished, press play to check your work. Find the distance between a 0.3 kilogram billiard ball and a 0.4 kilogram billiard ball if the magnitude of the gravitational force is 8.92 times 10 to the minus 11 newtons. Pause the video, and when you're finished, press play to check your work. The answer is 0.3 meters.